The next step is actually winding the transformer. The question is, what voltage do we actually want to wind it for? This inductive heater says that it pulls 1,000 watts at 48 volts. And this capacitor says that it can handle 17 amps of ripple current. So all we need to figure out is how much voltage to give this board so that this capacitor is only seeing 17 amps. To do that, we're going to assume that the voltage and current are proportionally related on this board, which is a fair assumption. And then we'll just take the ratio of voltage to current. So the first thing I did was divide the 1,000 watts by 48 volts to get 20.8 amps. Then the next thing I did was just take that 48 volts, multiply by the ratio of the amperage we want to work at, divided by the amperage that it's going to draw at full voltage, and I got 39.2 volts. And this is going to be a safe estimate, so the next step is figuring out how many feet of wire, approximately, we're going to need to wind the transformer like that. Here we've got everything wired up exactly like it was in the microwave, with the exception of I might have cut out a sensor so that this thing wasn't dependent on that to work. And I shorted this relay together. So what I'm going to be able to do is turn the transformer on and then measure the voltage that I get off of one loop of wire. I've got a loop that I'm sure that it goes all the way around. And it measures 0.9 volts AC RMS. Get to the number of turns. I just divide the 39.2 volts peak that we're looking for by the 0.9 volts RMS times 1.4. Without getting too hung up on AC, where that 1.4 comes from is when we're looking at a sinusoidal waveform, which is what AC current is, we get a peak voltage, but then we also get sort of the average voltage, the root mean square voltage. And this is what we're used to thinking of AC line voltage when we say we've got 120 volts. That's an RMS value. That's what the meter's in, but it doesn't represent the value that this capacitor is going to see. So we're going to go with the peak voltage value. So then I just measure the length of the wire that I use in that loop, and multiply it by the number of turns, and I get an estimate for how many feet of wire it's going to take. Remember, I built this loop a little bit big because the last thing I want is to spend a bunch of time wrapping a transformer with wire and then find out that I don't have enough at the end. When we get close to getting done wrapping the transformer, I'm actually going to take this and hook it up to a rectifier, hook it up to the capacitor, see if the voltage is right. Because that meter isn't really designed to be accurate at that low of a voltage level. When I wrap this transformer, I want it to be really tight. So I screwed the transformer to a board. That's going to keep it from moving. And then I've got a clamp here set up that I can stick that wire in so that it doesn't move around either. What I'm going to do before I start wrapping is stick these little paper guides into the sides of the holes rather in the transformer, and they're going to keep the wire from cutting itself on this edge. Like I said, when I was pulling this transformer apart, it'd be nice to leave the paper there, but I couldn't do that. It ripped when I was taking the coil out. And finally, I've got these shims that are going to make sure that the wire goes straight out and again doesn't touch that edge. And I'm going to use this little piece of a stirrer stick to make sure that this thing gets a radius. This is sort of how that's going to look to the wire. The wire is going to wrap around like this so I can hold it tight and I'm not bending the wire around a corner. Before I get too deep into winding this transformer and checking voltages, I wanted to remind everyone I'm working with dangerous voltages and currents. Just because I use the word we doesn't make this a DIY video. It's for info and education only. As we'll see soon, high currents can heat things super hot in a split second. The reason I want to get this wrapped so tight is because when this transformer is on, any wire that it's putting a current into is going to experience a force. This is what that looks like. Over time, that's going to be able to vibrate and that gets hot. But over time, that's going to be able to vibrate and it could mess up the wire, it could damage the insulation. So I'm going to keep I'm going to keep that tight. Wrapping this transformer was about a 4-hour process, and even with the highest speed setting that I've got, it was unwatchable. So I'm going to go through pictures instead. In this picture, you can see how that card lines up with the shims, so that the wire doesn't get incorrectly bent or rub against the side. This is a picture of how I start out the windings. Basically, I've got that wire pushed through to the midpoint so that I've got equal distances to go through, and basically that keeps me from having to wrap like 31 feet through a hole every time I make a turn. I clamp it down so that there's tension on it from the beginning, and then I'll tape some wood to a screwdriver and actually go in and press the wire to work it into position so that it's all tight. And then after every layer, I'll go through, I'll take some little strands of solid wire, and I'll wrap them around that layer to hold that layer together so that it doesn't come undone when I'm doing the next layer. Because each layer, I'm putting a lot of force on that wire. So as the transformer is getting wound, even though we can get things really straight using that screwdriver to press against it, what we'll notice is that the coil itself is actually moving a little bit around the core. So to fix that, I'm just going to stick a shim in it and then pry against that from the other side. Periodically, when I was wrapping that core, I would stop and check the voltage that I was getting out. So basically, I'd just take those two wires that were coming out of the transformer and connect them up to the bridge rectifier on the AC side, connect the other side to the transformer. I also connected a light across the capacitor that I could screw and unscrew in order to discharge that capacitor. Now once I got up to that 39.2 volts, unloaded that is, I stopped and soldered some terminals onto the wires that were coming out so that I could hook up the inductive heater itself and see what the voltage was like when the inductive heater was running, because we didn't really plan on, calculating for core losses in the transformer or copper losses or anything like that. So I just wanted to find that out empirically. Now there's a good reason for me to take these two different measurements. The voltage that I measured before, when it was just the rectifier and capacitor connected, is known as the open circuit voltage. And I've got to keep that underneath 48 volts to make sure that the capacitor is not seeing too much voltage, and for that matter that the ZVS isn't seeing too much voltage either. The underload voltage, which is what I measure with that ZVS connected, gives me the average voltage that's going to the system. So I'm going to get the average amperage that's going to the system, which is what I really care about for that capacitor. The reason it's important for me to take these two voltages is because that underload voltage is an average value. If I'm just seeing 39.2 volts under load, I might still be getting voltage spikes that go up above 50. I had to stop a little bit early because the open circuit voltage that I was getting too close to 50 volts, which is the limit for that board and that capacitor. So the operating voltage is a little bit under 39.2. Once everything is wrapped, I take out those little guides, those little wires that I use to secure the windings, the layers. The trick that I do is I'll push them through to the bottom side, and I'll snake that out, and then I'll pull them out from the bottom. What this enables me to do is cut off the part that's all bent up, like where I twisted the wire together, so that part doesn't have to try and go through a bunch of tightly wound coils.